everybody. Welcome back to Monte Carlo Methods. When we last left off, we were testing our random number generator for uniformity and independence. And I said that we would do one more video, which would be this one. But as I was putting this together, I thought about it a little more, and I need one more after this. Now, if you want to skip this video and the next, by all means do so you can get to the Monte Carlo. How do I simulate things? However, I think that these two videos are still important even if you don't care about testing your random number generator, because several of the tests we're talking about here can be adapted to other univariate distributions. So maybe you have some particular distribution with a PDF that no one's ever seen before and no one's given it a name, and you want to simulate values from it, and you want to check whether or not you're doing the right thing and simulating values from the right distribution. And also maybe you care about simulating independent values. So you can adapt this test for independence that we're going to talk about today for your distribution. So that's why I don't think that this is a waste of time. If you want to skip ahead, by all means do so, but there's good stuff here. And what I have today is one relatively short test, and then I'm going to talk about the chi-squared goodness of fit test, which is not for anything in particular today, but most of the tests in the next video, and there will be several in that one, are based on a chi-squared goodness of fit test. So I want to get that out of the way today so that we're ready for the next video. So one short test and then a sort of aside, which won't be too long either, into the chi-squared goodness of fit test. Okay, so in the last video, we were talking about runs tests for independence, and we were looking at runs up and down in our data. In today's video, we're going to look at runs above or below the mean. So let's say we were trying to test whether or not our sampled values came from a uniform 0-1 distribution. The mean for that distribution is right in the middle at 1/2 because it's a nice flat line, well-balanced distribution. There isn't like more mass on one side or the other, which will drag the mean around. Again, the mean of the uniform 0-1 is 1/2. So if you look at values coming out of your random number generator, and you see a value maybe above the mean, and then another one above the mean, and then the next one's above the mean, and the next one, when does it start to seem suspicious for independence or uniformity for that matter? This is the idea behind today's test. We're going to say, I hope that we're not above the mean or below the mean for too long. And yeah, it's as simple as that. So let's get right into it. I've got my same 21 values that I had in the previous video. These were simulated using the built-in random number generator in R, which happens to be a Mersenne twister. And just like in the last video, you should read these numbers. This is the order they came out in across rows. So this is the first number generated, the second, third, fourth, fifth, sixth, seventh, etc. That is important because we are looking for independence, right? And if you think that your random number generator is keeping some kind of correlation between the values, one thing you could do maybe is shuffle them all, and you would lose that. But you don't want to have to work with shuffled random numbers for your Monte Carlo algorithms, because often they will take millions and millions of values from the random number generator. So you just want to draw one as needed. You don't want to have to store a whole bunch and then worry about shuffling them. So keeping them in order is important here to see any possible kind of correlation between the numbers. And correlation independence, not exactly the same thing, as you may know. But I think the word correlation maybe makes a little more sense in this context. Like if you're seeing as one goes up, then the next number tends to go up. That's a correlation kind of thing, as well as a dependence kind of thing. Now let's count runs on this slide above or below the mean. Again, the mean is 1/2. So if you look at this first value, it is below the mean of 1/2. And the next value also below. And the third value also below. And the fourth value over here is above. So this mean, or this run below the mean of 1/2, ends right here. It consists of these three values. What I have is a run of length 3 of values below the mean. Just like in the last video, I actually don't care about the length of these runs, but I will in the next video. So why not talk about the length? Because it's different here than it was before when we were talking about runs of increasing and decreasing numbers. Because to have numbers be in an increasing run, when you look at any particular value, you do need to sort of know what's around it. Whereas if you look at any number in here, if it's above the mean, you know it's inside a run above the mean. It could be starting it, it could be ending it, it could be right in the middle, but it's a lot easier to see whether or not, well, it's super easy to see whether a single value is above or below the mean. You don't have to look at values around it. So we count the length of these runs differently. Again, I don't need length of runs for this test, but if we had 3 numbers that were increasing in a row and then the 4th number went down, we really would say it increased once and then it increased again, and that would be a run up of length 2, even though it consisted of 3 numbers. Whereas here, when we're looking at being above or below the mean, we would say in this case that we have a run of length 3. Now let's go to the next value. When we start over here, we are above the mean, and the next one is also above the mean, but the one after that is below the mean. So we have a run of length 2 of values above the mean of 1/2 for the uniform 0-1 distribution. I think you probably get it by now, but I do want to look at just 2 more to point one thing out. So the next value is below the mean, and we're starting a run below the mean. And the one after that is below the mean. And then over here, we have one above the mean. So this is a run of length 2 of values below the mean, and then it's over. And the thing I wanted to get to really was the next value. The next value over here is above the mean, and it's actually starting a run above the mean, but the one after, the number over here, is below the mean. So we do have a run of length 1 above the mean, consisting of a single number, and that's okay. So when you think of runs, you think of a lot of consecutive values in a row, but you can have a run of length 1 here, and it will consist of one number, whereas a run of length 1 in the increasing decreasing test did involve 2 numbers. Okay, so if you go through this slide, again, there's 21 values here, and count the runs above the mean and below the mean, you'll find that there's 5 above the mean and 6 below the mean, for a total of 11 runs above or below the mean. And this total is all we really care about. We're not going to care today about distinguishing between whether the runs are above the mean or below the mean. And if you'd like, pause the video here and count your runs and make sure you get the same thing as me. Okay, so let's get into the detail and a little more theory here. I'm going to let capital X1 through capital Xn be a random sample. This means they're IID of size n from any continuous univariate distribution with a PDF, little f, and a CDF, cumulative distribution function, capital F. I'm going to let R sub n, I'm going to reuse that notation from the last test, be the number of above or below the mean runs in the sample of size n. The question is, if things are independent, what do we expect Rn to be? And there's a little bit of, if things are uniform, that's also part of this test, because although we can change this test for different distributions, our expectation here is going to depend on the fact that these data are coming from a uniform distribution. So it's a test for independence, but it does rely on the fact that the probability of being above or below the mean for a uniform distribution is 1/2. This test is adaptable to other distributions, though. So what do we expect Rn to be in statistical notation? What is the expected value? This E of R sub n. Again, this is going to be specific to the uniform 0-1 distribution, but it can be adapted. So note that if you have a uniform 0-1 distribution, the mean for that distribution is 1/2. And the probability that a uniform 0-1 is above this mean or below, or even greater than or equal to or less than or equal to, is 1/2, because the interval 0 to 1 is cut in half with that 1/2. And the flat line distribution, we are equally likely to be above or below. So the probability of being above is 1/2. Whereas if we were talking about maybe x having an exponential distribution with some rate lambda, the expected value or mean there is 1 over lambda. And if you want to compute the probability that x is greater than 1 over lambda, if you know the exponential CDF, use that. But in general, you would integrate from 1 over lambda to infinity the exponential rate lambda PDF, which is lambda e to the minus lambda x dx. and you will end up with e to the -1. So don't fall for the trap of thinking that the probability you're above or below the mean for a distribution is 1/2, because I think you're thinking about a median. So let's get specific. Let's let capital X1 through capital Xn be a random sample or IID values from the uniform 0, 1 distribution. I want to come up with an expression for the total number of above or below the mean runs, which we're calling Rn. And just like in the last video, I'm going to basically look at each value in my sample and figure out whether it's starting and above or below the mean run using indicators. So for I equals 1, 2, up through n, I'm going to define the indicator random variable, capital I sub lowercase I, to be 1 if capital X sub I is starting and above or below the mean run, and 0 otherwise. And then, of course, the number of runs, the R sub n, is the sum as I goes from 1 to n of the I sub I, and the expected value of R sub n is the expected value of the sum. And it's a linear operator. You can pull the sum out, so the sum of the expected values, and we're left trying to compute something very similar looking to what we did in the previous video. Now, note that capital X sub 1, the first value in your simulated values, in my case from the random number generator, is always starting a run above or below the mean. And so I sub 1, the first indicator, is always 1. However, unlike the last test we did, where the last value in the sample, the X sub n, could not start a run, it is possible here that it could start this kind of run. So convince yourself if you need to. What I have here are some numbers representing the last 3 values of my n sampled values. And you see here I am below the mean of 1/2, and I am here as well. But here I am now above the mean of 1/2. This is my X sub n realization. And so X sub n is starting a new run here. Whereas when we were talking about increasing and decreasing, I couldn't tell you that Xn is starting a run up because I would need Xn plus 1, and we didn't have that in our sample of size n. But you definitely can have the start of a run above or below the mean with the final X sub n in the sample. So let's look at the expected value of that indicator first, because it kind of seems like it might be a special case. Spoiler alert, it is not, but let's look. So the expected value of I sub n is 1 whenever X sub n starts and above or below the mean run, which I'm going to write like this, above/below run, and I'm not going to write the mean because it's a lot of stuff to write down. An indicator, again, the expected value of an indicator is always the probability of the thing it's indicating, which is Xn starts and above or below the mean run. So this can be broken up into 2 cases, whether it's either starting and above the mean run, or disjoint event, it's starting and below the mean run. So we get to add those probabilities. And in order to have us starting and above the mean run, what do we need? We need Xn to be above the mean, and we need it to be not within another run above the mean. So this means we need Xn minus 1 to have been below the mean, so that not only is Xn above the mean, but it is starting a run above the mean. Similarly, if Xn is starting a run below the mean, we need it to be below the mean, and we need the previous value to have been above the mean so that Xn is starting this run below the mean. And these values are presumably independent. We're doing like a hypothesis test, and under the assumption of independence, the null hypothesis, that's how we want to work out what to expect to see. And then we can see what we actually see and how it compares. So by the assumption of independence, I can break up this joint probability here. This comma is like and in probability. And I can break it up into a product of individual probabilities in this one as well. So that's all I'm doing here, but I don't want to write all that stuff out. So I just have some squiggly lines in here. This represents the probability of this times the probability of this plus the probability of this times the probability of this. And what is the probability that a uniform 0, 1 is above the mean or below the mean? We just said that that was 1/2. So plugging in all these 1/2s, we end up with 1/4 plus 1/4. We end up with 1/2 for the expected value of I sub n. So I looked at the nth value in our sample first because I thought maybe that would be a special case, but we're going to see it not really. So let's try to get the expected value of the ith indicator, the expected value of I sub I. This is one if and only if the random variable x sub I is starting a run above or below the mean. So the expected value of an indicator is always the probability of the event being indicated. And just like we just saw, for x sub I to be starting a run above or below the mean, we could break this up into two disjoint event probabilities where we start a run above the mean or we start a run below the mean. And now to get into the weeds with the individual x's, what needs to happen? If x sub I is starting a run above the mean, then it needs to be above the mean. And also, previous value needed to be below, or x sub I would be just within a run above the mean, not starting the run. Similarly, for the below case, if x sub I is starting a run below the mean, then we needed x sub I to be below the mean, and we need the previous value to have been above the mean. Just like before, I want to use independence here and break this up into a product of two probabilities over here plus a product of two probabilities over here. And every one of these probabilities is 1/2. So once again, we end up with a total of 1/2. So it turns out the x sub n value was not really a special case in terms of the expected value of the indicator as to whether or not it was starting a run above or below the mean. So what were we trying to do? We were trying to figure out what to expect for that number of runs. On my slide of 21 values, I saw 11 runs. The expected value of r sub n is the sum as I goes from 1 to n of the expected value of the indicators. The first indicator is always 1, so let's pop that off the end there. And then we have a sum as I goes from 2 to n of 1/2. This is n minus 1 different values. It's 1/2 plus 1/2 plus 1/2, n minus 1 times. So the sum is n minus 1 times 1/2. And when you add this all up, you get n plus 1 over 2. Wow, I didn't mean for that to happen. But when n was 21, I get 22 over 2. I get exactly 11, which is what we saw. But that was some good luck right there, because there's definitely variability. And this is what we need to talk about next. Because we're going to use the central limit theorem again and say that because this Rn is a sum of a bunch of random variables, it should act approximately normal for large samples. This is a convergence and distribution approach. So I'm going to write it like this: Rn, and then the squiggly line has the distribution with the abbreviation approx across the top, approximately normal with mean n plus 1 over 2 and some variance. Now, the variance calculation was so bad last time that I put it after the outro of my video, pretty much to discourage people from watching it. This one is not so bad. I might regret this, but I claim that these indicators are independent. They definitely were not in our previous video where we were looking at runs of increasing and decreasing numbers, but they will be here. And if we can show this claim, then the variance of a sum of indicators would just be the sum of the variance of the individual indicators. You can pull sums through variances if you're working with independent things. Now, to prove this claim, in order to do that, I think is maybe just as much work as not assuming they're independent and taking the covariance double sum approach that I took in the outro to the last video. But I thought, let's mix it up. We've got independence supposedly, and let's show it. Let's do something a little bit different here. So I claim these indicators are independent. Now, what this means is that for all I, and indicator I1 is out of the picture. That's not even a random variable. So for all little I equaling 2, 3, up through n, and all j, index j, not equaling I, because an indicator is never going to be independent of itself. So I want to look at like an indicator I sub I and I sub j, where those subscripts are different. We need to check that the joint probability that, say, I sub I is 1 and I sub j is 1 factors into the individual probabilities of that happening. But we also need to check the probability that I sub I is 1 and, say, I sub j is 0 factors into those individual probabilities. And I sub I equals 0 and I sub j equals 1. And finally, I sub I equals 0 and I sub j equals 0. And actually, you can get one of these for free, because these probabilities need to add up to 1. So you really don't need to check all of these, but it is a lot of checking, and it will depend on your values of I and j, or more specifically, it may depend on how far away j is from I. We saw something like that last time. So there's actually a lot of cases for us to check here, and I am just going to check one of them and then call it good. Now I want to check what I think is one of the most suspicious cases, and that is when j equals I plus 1, or equivalently I minus 1, when the indicators are right next to each other. Again, an indicator is not going to be independent of itself. We know that, and that's not important for pulling the sum out of the variance. We need the I2, I3, I4 up through In, those to be independent of each other. So let's look at the case where j equals I plus 1. And I want to look at, I'm just going to look at the first one of these joint probabilities. So even this case, I'm not going to fully complete because it's just more of the same. Once you see this, I'm sure you can do the rest if you care to check. So let's look at the probability that I sub I equals 1 and I sub I plus 1 equals 1. Now, when do these things happen? This will happen if and only if the ith value in my sample for my random number generator, my x sub I, is starting an above or below run, and at the same time, and comma, x sub I plus 1 is starting an above or below the mean run. Oof, so a lot of cases within this one case, to compute this, I can look at the probability that xi starts an above the mean run and x sub I plus 1 starts an above the mean run. And I think you're already realizing there's something wrong there. That actually can't happen, because if you're starting it above the mean run and the next value is still above the mean, it wouldn't be starting the run. So some of these probabilities are 0, but here are 4 cases we should be considering. And yeah, this will be 0 and this will be 0. So let's look at the other 2. I don't know if everyone can see the colors I'm using, but I've color coded this one in this kind of yellow color and a kind of green color here. And I'm going to try to keep the color coding going through the end of this little proof within a proof. Okay, so the next thing I'm going to do is what we already did in today's video. How does x sub I start an above the mean run? Number 1, it needs to be above the mean, and number 2, it needs to be the start of that. So x sub I minus 1 needs to be below the mean, in this case of 1/2. So here I am just writing this all out. When I say x sub I minus 1 is b and x sub I is a, then I'm just saying is below the mean and is above the mean. So b for below and a for above. And I'm not bothering to write the mean because there's only so much that can fit on this slide. But if I want x sub I to start a run above the mean and x sub I plus 1 to start a run below, then I need x sub I to be above, I need x sub I plus 1 to be below, and I need x sub I minus 1 to have been below, or x sub I would not be starting the run. So this is what you get when you think about what it takes for this event up here in this yellow line to occur. Similarly, the green line, if I want x sub I to start a run below the mean, it needs to be below the mean, but the previous value, x sub I minus 1, needed to be above the mean. And if I need here x sub I plus 1 to start a run above, then it needs to be above. And so that's what I'm saying here in this wildly abbreviated notation. But the assumption is that things are independent. Again, we want to see how our statistic, R sub n, behaves when things truly are independent. So I get to break these up into products of individual probabilities, and we know all of these probabilities are 1/2. So we get 1/2 cubed plus 1/2 cubed for a total of 1/4. So if you recall, what we just computed is the probability that I sub I equals 1 and I sub I plus 1 equals 1, and we got 1/4. And we already know that the probability that any individual indicator is 1 is 1/2. So we do, in fact, have 1/2 times 1/2 equals 1/4. So we have that this joint probability is the product of these 2 individual so-called marginal probabilities, which is good for independence. 1 out of 4 cases for 1 case of j being I plus 1. Lots of other things to check, but it's all pretty straightforward. So let's go back to our total variance calculation. R sub n was 1 plus the sum as I goes from 2 to n of I sub I. The variance of R sub n is the variance of this quantity. Having a 1 plus doesn't affect the variance. If you have a random variable and it has a certain amount of variability and then you add 5 to it, the variability has moved up here, but it doesn't change how variable it is. So we can drop the 1 plus. We've got the variance of a sum as I goes from 2 to n of I sub I. We have just kind of proven, we proved one small case, but if my claim is true, and it is, we can pull the sum out of the variance using independence. Now, what is the variance of I sub I? The variance of I sub I could be written as the expected value of I sub I squared minus the expected value of I sub I quantity squared. The indicator squared is just the same thing as the indicator because it takes on the value 1 and 0. So you see here I've dropped this squared. We know the expected value of I sub I is 1/2. So this is 1/2 and this is 1/2 squared. And we end up with 1/4. And so if you pull it all together, we've got n minus 1 terms here, each with a variance of 1/4. So the variance for R sub n is n minus 1 over 4. So in summary, for a large sample size n, usually considered n greater than 30 or greater than 40, but why push it? Get a larger n. Our Rn by the central limit theorem is approximately normally distributed with mean n plus 1 over 2 and variance n minus 1 over 4. If you paid attention in the last video, you'll recall that I did not try to say, R sub n is pretty much a sum of Bernoulli random variables, and that would be binomial. I couldn't do that then because I did have dependence between the Bernoulli random variables. I don't here, so I could say that R sub n is a binomial random variable plus 1, basically, and I know how to compute probabilities for things like that, but no one really bothers. This is just one small test in what I would say is a suite of tests. And so if you want to make this an exact small sample test, you could. But presumably when you're testing like your random number generator or your simulation, you are producing a lot of values and it's just easier to go with the normal distribution. So what are we going to do? I'm going to define a random variable z sub n to be Rn minus this mean divided by the square root of the variance or standard deviation. And by the central limit theorem, this is approximately a standard normal random variable for large samples. Again, this is a convergence and distribution result if you know what that is, but it's not that important. Now, if you look at a standard normal distribution, the bell curve centered at 0 with standard deviation 1, you know that if you go from the values negative 1.96 and 1.96, you can trap area at 0.95 right there in the middle. So what I'm trying to build is kind of like a 95% confidence interval here. I'm going to say that Zn is between negative 1.96 and positive 1.96 with approximate probability 0.95 because Zn is not exactly a standard normal. And I'm going to plug in my expression for Zn here. And then I'm going to try to isolate my Rn in this inequality. In the end, we end up with, for large n, we expect that Rn, the number of runs above or below the mean, to be in the interval n plus 1 over 2 plus or minus 1.96 times the square root of n minus 1 over 4, roughly 95% of the time. In the case of 100,000 values, which is my favorite number of values to simulate, this interval happens to be 49,690.6 through 50,310.4, just to give you an idea of what would be acceptable values for the number of runs in your sample size of 100,000. Sometimes you won't be in here. If everything was exact, 5% of the time, if you ran the simulation, got 100,000 values, threw them out, got a new 100,000 values. If everything was exact, some of those run counts should not fall in here, 5% of them. Plus, we have here lots of approximations and large sample kinds of things going on. So even more might not be in here. And again, this test is pretty weak for independence. Our calculations depended on it being on the values from the sample being independent, but they also happen to depend on them being uniform. So we're looking at things that are consistent with independence, and in this case, uniformity. And so I would include this in a large suite of tests that I would run all together to test my random number generator. And that is the end of the runs above and below the mean test. I actually think this would be a good point to cut this video, but I keep promising you that we will end this testing phase, and I've already dragged it out into another video. So let's press forward and talk about the chi-squared goodness of fit test so that we can use this next time. The chi-squared distribution is a special case of a gamma distribution. If you know about that, you've probably already heard of a chi-squared test, but if not, a continuous random variable x is said to have a chi-squared distribution with n, and n is a positive integer, and degrees of freedom. And that's just a parameter. So it's like p for the Bernoulli distribution or a mu and sigma squared for a normal distribution, and has the name degrees of freedom for reasons that I don't want to get into today. It's just a parameter. But it has this chi-squared distribution with n degrees of freedom if it has the following probability density function. In here, I have a gamma function, which is different than a gamma distribution. And we could talk about that. I'm not going to talk about it today, but it's a constant. And you can really see how this PDF acts by looking at the X part. Let's take a look at some pictures. But before that, I just want to say that we write the random variable X squiggly line has the distribution, and then a chi-squared symbol, open parentheses and close parentheses. So here are some pictures as promised. This is a chi-squared PDF when n equals 3, n equals 5, and n equals 10. So you can see that kind of mass sort of being pushed down and out. And if you take mathematical statistics, you will learn so many cool things about the chi-squared distribution. For example, if you take a standard normal 0, 1 random variable and square it, that has a chi-squared distribution with 1 degree of freedom. And if you add independent chi-squared random variables, you get a new chi-squared random variable with the degrees of freedom coming from adding the individual degrees of freedom. The chi-squared distribution is all over statistics, and there's so many great things to know about this. I highly recommend taking mathematical statistics at some point if you haven't already. Okay, so towards this chi-squared goodness of fit test, I do want to talk about the multinomial distribution. If you've come from my math stat course, for example, I think we never actually talked about this, so this would be a good time. It's very similar to the binomial distribution. It is a generalization, as we will see. So suppose you have n independent trials of an experiment. For a binomial distribution, I would then say, and each trial can result in 2 possible outcomes, success or failure. This is a generalization, and I'm going to say that each trial of your experiment can fall into one of k possible outcomes or categories. So success or failure would be 2 categories. K would be 2. This is a little more general. Now, we're going to assume this is a parameter for the model that the probability that any trial falls into category I is going to be some probability lowercase p sub I. And so we have a little p sub 1, little p sub 2, up through little p sub k, and those need to sum to 1. Finally, for I equals 1 up through k, I'm going to define capital X sub I to be the number of outcomes in the total of n, or the total of n trials that fall into category I. Note that my random variables capital X1 through capital XK have to sum to n because there's a total of n tries, and then we're throwing those tries into one of k buckets. And so if you count the number in the first bucket, the second bucket, and third bucket, and add them all up, there's a total of n. So these are definitely not IID random variables at all. They're quite dependent. And yeah, so this is not a random sample from anything. But when k is 2, as I said, we could call the category success and failure, and we're talking about a binomial distribution. And you can let x1 be the number of successes and x2 be the number of failures. And when you do study the binomial distribution, you never look at it this way. You just say x is the number of successes because the number of failures is then locked in. It's then n minus x. But I do want to write down the binomial probability mass function a little bit differently so we can generalize to the binomial probability mass function maybe a little bit easier. So if x1 has this binomial distribution with parameters n and p, 1 in this case, but it could just be p, right? Because I have a p1 and p2 in this little mini example, they have to add up to 1. So really there's only one parameter here, p, and then p2 would be 1 minus p. But again, I'm trying to sort of match a multinomial sort of probability mass function. But as you probably know, if you're here, the probability that my x1 equals some little x1 is going to be n choose little x1, p1 to the little x1, 1 minus p1 to the n minus x1. And if I write out this n choose x1 in factorials, I get this. And let's rewrite this whole thing by, and by the way, little x1 can take on values 0, 1, 2, up through n. The total number of successes in n trials can be 0 successes up through n successes. So now let's write this a little bit differently. I'm going to look at the joint probability that capital X1 equals some little x1 and capital X2 equals some little x2. Now, if these two small x's do not add up to n, then this is not happening, and this probability is 0. So if we assume that little x2 is in fact n minus little x1, then we get an actual non-trivial probability here. We get n factorial over x1 factorial, also in the denominator x2 factorial, p1 to the x1, p2 to the x2. This is exactly what I have up here, just sort of expanded with different notation because, right, little x2 is n minus little x1, etc. And it is this version of the binomial probability mass function that I think is most useful in looking at the probability mass function for the multinomial distribution, which is more general. So in general, for the multinomial distribution, the probability capital X1 equals little x1 dot, 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 out through capital XK equals little xk looks like this. You could take it as a definition of the probability mass function for the multinomial distribution. And we do need these little x's to sum to n, and we do need these little p's to sum to 1. And one of these, in both cases, one of these is locked in, right? Because these sum to n and these sum to 1. So as for the parameters of this model, the little p1, little p2, you only need to specify k minus 1 of them. Of course, the probability is 0 otherwise. And so with that, I do claim this has something to do with the chi-squared distribution. In fact, for the multinomial distribution, capital X sub I, as you know now, is the number of outcomes out of n that fall into category I, and the expected number of outcomes to fall in category I, which I could write as the expected value of X sub I, is, so you have independent trials, you're putting things into categories or buckets, and you've got n of them, and the probability you fall in the ith bucket is P sub I, so you expect n times, that proportion, n times P sub I, to fall into category I. That is the expected value of X sub I here. And so I'd like you to consider a new random variable. I'm going to call it W, and I'm going to define it to be the sum as I goes from 1 to k of X sub I, capital X sub I, minus n P sub I squared divided by n times P sub I. I claim, and it is beyond the scope of this course, it's a very math stat problem, that when there are many outcomes expected in each of the k categories, that this random variable W will have an approximate chi-squared distribution with k minus 1 degrees of freedom. Again, just a parameter for the chi-squared. Where does this come from? If you've had some math stat, it doesn't exactly look like it, but we've got binomial random variables, and those are sums of Bernoulli's, and the central limit theorem telling us that's normal, and the fact that a standard normal squared is a chi-squared 1, and when you add independent chi-squareds, you get a new chi-squared. That's kind of where this is coming from. There's a little more to consider here because the individual chi-squareds are not independent, because there's quite a relationship going on between each of these terms in the sum, especially because all of the capital X's have to sum to n. So there's a little more going on than that, but that's the basic idea. And I'm not going to prove this claim here because this is not a math stat course. By the way, the rule of thumb for many outcomes distributed into the categories is not really, it's not really like that n itself is large. That's not enough to say like n is greater than 30. The rule of thumb that's generally considered safe is for the expected number to fall into each of those k buckets to be at least 5. So n times P sub I greater than or equal to 5 for all I equals 1, 2, up through k. Now, our X sub I is the number of outcomes that fell into category I. And you can think of that as your observation after you have sort of divvied up your n outcomes into buckets. And this W is usually written like this, where this capital O sub I stands for the number observed in category I, and this capital E sub I stands for the expected number in category I, which was n times P sub I. So you'll often see this. This is exactly what we just did with O sub I for observation in place of X sub I, and this expected number in the ith category in place of the actual expected number, which is n times P sub I. So this thing is approximately chi-squared distributed with k minus 1 degrees of freedom, as long as the expected number in each of the k categories is large enough, is at least 5. Okay, so I'm definitely out of time, but I want to give you a little coming attraction, how we might use this to test for uniformity or independence in the next video. Remember the equidistribution problem and the RAND-U IBM random number generator? That was a nice 3D problem to look at, But think about the 2D problem again. So suppose I generate 100,000 values from the uniform 0, 1 distribution using a random number generator, and maybe take the first and second value and make an ordered pair, and the third and fourth and make an ordered pair, etc., and plotted those 50,000 ordered pairs in the plane between x equals 0, 1 and y equals 0 and 1. So a unit square, if you will. Now, if those are really uniform and independent, they should be scattered really well in that square. They shouldn't be all in one part, or there shouldn't be sort of big holes in the plot if you have a lot of values. So one thing we can do is we could say, I'm going to chop up my x-axis between 0 and 1 into 10 equal intervals, and do the same thing with my y-axis, thereby defining 100, so 10 by 10, 100 equal area subsquares in my unit square. Now I throw those 50,000 points in there, and if everything is good and uniform and independent, how many do you expect to see in any one of those subsquares? So I've got 50,000 divided by 100. I expect to see 500 in each of those subsquares. What do I observe? I'll have an observed number of ordered pairs, and I'll have my expectation or expected number, and we can make a chi-squared kind of statistic to test for uniformity and independence kind of at the same time, to test whether or not the data is consistent with uniformity and independence. This is why we need the chi-squared goodness of fit test. I have so many tests in the next video that are going to depend on this kind of statistic. So I hope to see you in the next one.